Everyone. Today's lesson is going to be about the properties of liquids. And if you recall from last week, we were talking about gases. Gases, when they are under enough pressure or they lose enough temperature, remember temperature is kinetic energy. When they lose enough kinetic energy or enough pressure is put on them, they can change state and they can come down into a liquid phase. We saw that on the phase diagram. And now today we're going to spend some time looking at liquids and how liquids behave. Before we get into the details, I wanted to take a quick second and look at this little um, outline that I have for you guys. So today we're going to be looking at the properties of liquids, and there are four main properties of liquids. A liquid can diffuse, it can evaporate, it can form a solid, and it has surface tension. And we're going to look at each of those different properties in a little bit of detail. But I wanted to just kind of point out to you the way that the notes are going to be laid out. We're going to talk about diffusion today, and then we're going to talk about evaporation, and then we'll stop actually in the middle of evaporation, right around equilibrium, I think, for today. But all of these terms, vapor pressure is a consequence of evaporation. Boiling point is a special case of evaporation, and equilibrium is a condition in evaporation that we need to consider. So all of those kind of fall under that one concept of evaporation. And then we'll talk really briefly about how liquids can form solids. So we will start with the property of liquids that they can diffuse. So diffusion is the mixing of a gas or a liquid, any substance, through its random motion. So when liquids diffuse, if you imagine taking a drop of food coloring and putting it into a container like this one, or my mouse is going everywhere, and putting it into a container of liquid like this one, the drop of food coloring starts really concentrated in the center. And over time, even if you don't stir it, over time, that food coloring is going to diffuse throughout the liquid. Now, of course, you could speed that up. You could speed it up by stirring it or agitating it. That's a whole nother story for solutions. But we're talking about that these liquids will eventually mix and become completely even all throughout, completely evenly spread out with these dye molecules, these green dye molecules mixed between the red and blue water molecules, completely evenly spread out over time. And that's because of their random motion. Remember that the random motion is part of the kinetic molecular theory that says that all substances in all phases, all matter is constantly in motion, and that gases have the highest motion, liquids have less, and then solids have that vibrational rotational motion. So we're seeing this larger than solid but lower than gas amount of motion and allowing the liquids to diffuse. The second property of liquids that we want to look at is evaporation. And so I just want to make a little note here. We have now looked at diffusion and we have covered that. That's it for diffusion, mixing with the random motion. Now we're going to talk about evaporation. So evaporation is the case where a liquid starts to form a gas. When a liquid wants to evaporate, this is water molecules here at the surface. And so these little Mickey Mouse guys here are really water molecules. Those are the two H's on the outside and then the red oxygen in the center. And what we see is that right here on the surface of the liquid and the surrounding gas, these molecules are gaining energy, and they get enough energy that they're going to jump out of the solution and up into the gas state, into the gas phase. And we call that process evaporation. So it's the process in which liquid molecules at the surface, and this is really important because it's different than boiling point. This is where liquid molecules at the surface finally have enough energy of motion, enough kinetic energy to leave and escape to become gas particles. So that's the process of evaporation. If you wanted to speed up evaporation, there are three ways to do it. One of them you see um, just, well, this is a blow dryer will do this one. This is the first type of evaporation. Sorry, I got them out of order in my mind. So heat is the first way to heat up evaporation or to speed it up. This is what we do when you blow dry your hair or you use a dryer to dry your clothes. A really good idea, just something that I use in my house. I don't know if you're ever in charge of doing dishes, but if you're in charge of doing pots and pans and you get them all clean, but you don't want to have to go through and dry them, they don't go in the dishwasher. If you just turn the stove on for a moment and stick them over the stove, that heat will evaporate all of the liquid off of them and you won't need to dry your pans, is one way to use this. A second way that we can speed up evaporation is to increase surface area. If you've ever been in class and you've put down a drink on the table, when you're not supposed to necessarily, and that drink kind of sweats onto the glass or onto the table, and you now want to take it off, you're leaving, but there's like this ring, and you don't want to leave the ring because you weren't supposed to. So you take your hand and you just kind of slide it through, and eventually it dries. That's increasing surface area. At sporting events, at volleyball games or basketball games, you often see this too. There's like a really big play and there's like some sweat on the floor. You'll see everyone come over and they start sliding their shoes on the ground. And what they're doing is they're heating up. Actually, they're creating some friction, so they're causing heat, but they're also increasing the surface area of that liquid, and so it will evaporate faster. And the last one you can do is you can add wind or air. Again, back to the blow dryer, right? The blow dryer or dryers for your clothes, they're doing both things. They're both heating and adding air or wind. But when we really add wind is if you've ever done your nails, when you get your nails completely all dried up and you need to, or all painted and you want to dry them and you do this little guy. You guys ever do that? Or that's the idea of adding wind to speed up evaporation rate. So you're trying to get the wind to hurry up and get those water molecules to get enough energy, kinetic energy, that they're going to leave and they're going to go be in the gas state. Oh, there's our drying nails. Okay. So we're now going to look at the special circumstance, um, the consequence of evaporation. When a liquid evaporates, the gas that is produced creates a vapor pressure. And so we're going to spend a little time trying to understand vapor pressure and equilibrium. So vapor pressure is created when gas particles or liquid particles are now left as gas and they're sitting above the liquid. Vapor pressure is usually described as the amount of pressure above a liquid. And that just means that it's that liquid that has evaporated up and now is causing a pressure. Remember, pressure is collisions. So what we're talking about when we say vapor pressure is we're talking about the collisions that are created by the gas after it evaporates. You might want to listen to that one more time. We're talking about the collisions from the gas that is created after a liquid evaporates. That's what we're talking about for vapor pressure. So we're going to look at a container. So this is a closed flask. This is like a Erlenmeyer flask used in chem lab. And what we have in here is we have a green liquid in the bottom and we've got these green little spheres down there. And these water molecules or these molecules on the surface want to leave and evaporate. And so you can see their little tails, see the like green circle, but then they have this like tail behind them. That's showing you that they have all of this energy and they're evaporating. And so when this gas leaves, it forms water vapor. So we've started with liquid water in the container, and a couple of water molecules have enough energy that they jump out and they form. At the same time, as this continues, some of the water molecules up here are actually slowing down and crashing back into the liquid state. If you've ever boiled a pot of water on the stove, the condensation collects on the lid of the pot and then kind of rolls back down into the pot below. And so that's an example of some of the water molecules are leaving as gas, while at the same time some gas molecules are condensing as liquid. When this number becomes equal, we have equal numbers leaving as falling back down. We call that equilibrium. So this is a moment, this is a special time or special consideration, circumstance of evaporation where we have equal amounts of evaporation and condensation happening at the same time. And so we say that the solution is in a dynamic equilibrium. Dynamic means that some molecules are still leaving and some molecules are still coming back. It's not sedentary, it's not stopped or fixed equilibrium, it's dynamic. Dynamic means in motion. So they're going to reach this dynamic equilibrium. So here we see the water molecules at the bottom of the flask at the beginning, and then we start to see those water molecules start to gain enough energy that they jump out of the liquid state and they're bouncing around. And finally here, we've reached a moment where we are in exact equilibrium. And the way they show that in the drawing is that they have exactly two molecules coming up and exactly two heading down and two heading left and two heading right. And so they really tried to balance everything out so that you can see that the molecules are all in exactly the same positions because this is sort of that moment of equilibrium that has been reached. Once we've reached equilibrium, we could continue to raise the temperature. And when you continue to raise the temperature, what you're doing is you're starting to reach something called a boiling point. So at equilibrium, we have a certain amount of pressure up here, and that pressure is pushing on the stopper and it's pushing on these container walls. If we heat up this gas enough, so I'm going to draw my really bad heat up here, okay? If we heat up, oh, maybe I'm not going to draw. Okay, if we heat up this gas enough, what we can do is we can create a situation where this gas, now the vapor pressure is equal to the pressure of the atmosphere. And so what that's doing at that moment is what we see that the liquid water, the gas particles of the liquid water that are pushing up, I can't draw it on here either, are pushing up so high and the energy is so high that it's now equal to our atmospheric pressure. And at that moment, every single molecule in the liquid is all going to try to leave at exactly the same time. And this is the boiling point. It is a special temperature, they say, a special temperature where all of the liquid is all trying to evaporate at exactly the same time. And the reason how this is different than just evaporation is that evaporation, remember, is just at the surface of the molecule, where boiling point is every single molecule all throughout, all trying to leave all together, a max exodus. And the reason why this is important is you're going to see those two terms in vocab, both on the vocab quiz and on the test, and you're going to need to know the difference. Evaporation is on the surface, boiling is from within that solution. Okay. All right. Well, that is all we're going to cover for today. We will pick up on this exact same topic tomorrow. We'll talk about when boiling point leads us to equilibrium and shifting the equilibrium, and then we'll finish up by talking about how they can form solids. So I hope you guys have a great day, and I'll talk to you tomorrow. Maybe. Okay, I'm still here. Hold on. I can't leave.